think I got that. So, it's holiday season, and I see some of you are dressed up appropriately for the holidays. I try to as well. This is one of my favorite science lecture times. So this is the happens to be the third lecture I'm giving about aliens. So it's a very interesting topic. And what's more holiday festive than some aliens, right? All right.
The microphone needs adjustment.
Uh-oh, what's wrong? Am I scraping again? I hear. This thing just should be bearable. There, is that better?
Is it better?
Better, all right.
Thank you so much.
All right, I don't want to, okay, I'll stop breathing.
Only for half an hour.
Yeah. I don't have notes today, because I'm pretty familiar with this topic. How many of you remember my Drake equation talk from 5 years ago? You do, you know what it was. So there's about 4 of you who are here. So I've tried to update it with some of the latest information, but some of this will be familiar. If you get tired and need to doze off because you're familiar with the topic, I understand. All right, so today, okay, without further ado, let's begin our discussion of the Drake equation. Now, I know that many of you are math averse. Actually, math wasn't my strongest area when I was studying physics in college, and it's one of the reasons I didn't go on to get a PhD in physics, because I was not in love with math. So I have some sympathy for those of you who are not particularly enamored of it. But here on the bottom of the slide is the Drake equation, and we will be talking about that today and potentially solving it. What? Skeptics everywhere. All right, so the Drake equation was first dreamed up by this fellow, Frank Drake, who was born in 1930, Harvard and Cornell astronomer. He once had this bright idea of using the Arecibo radio telescope in Puerto Rico to beam a radio message out to a big cluster of stars. It's called a globular cluster. It orbits the Milky Way galaxy. He beamed this message. I don't remember the content of it, but essentially it said, "Hey, we're here. Are you hungry? Would you like to come for dinner?" Something like that. And so he used this telescope. Now, he did this back in the, I think, 70s. I don't know, Mike, if you remember. One of the things that scientists have subsequently concluded is that a globular cluster of stars has low metallicity. Now, astronomers have their own lingo, just like other scientists. And in the lingo of astronomy, a metal is anything besides hydrogen and helium. So carbon is a metal, oxygen is a metal, silicon is a metal, in the lingo of astronomers. So when an astronomer says that a star has low metallicity, it means that the stars mostly are just hydrogen and helium with not much else. And the stars in a globular cluster, any given globular cluster, tend to be low in metals, which means that they're not likely to have rocks and silicate-rich and metal-rich planets orbiting those stars. So it's likely that globular clusters are kind of this desert of planetary formation and whatnot. So it might not have been the best target for sending that message. However, depending on the reaction of potential recipients, maybe it was a great place to send the message. So Frank Drake had this question, which is, how many advanced alien civilizations may there be in our galaxy, or in the universe? But for today, we're just going to limit our discussion to the galaxy. And he came up with this Drake equation. Now, many equations in the sciences are what are called differential equations, because they relate the rate of change of one thing to the rate of change of other things. And those differences in the rates of change give rise to differential equations. That's not what this is. This is just a regular algebraic equation, and the little dots mean multiply. Some of you are familiar with the symbol x for multiply. Here we're using dots instead. And each of these symbols is just a variable. So it's one equation with 1, 2, 3, 4, 5, 6, 7 variables. And those of you who remember your middle school algebra will remember that to solve an equation with 7 variables, you need at least 7 independent equations. Well, we just have one, so we're going to take a wild guess at what the values may be. All right. Here's what the different terms mean. So I expect you to memorize this. R star is the rate of star formation. FP is the fraction of stars that have planets. NE is the average number of planets that can potentially develop life. FL is the number that actually do develop life. F of I is the fraction of those planets that have intelligent life. FC is the fraction of civilizations that develop technology on those planets. And L is the length of the lifespan of those advanced civilizations. And that's it. So we've got time for questions. I'm going to go through this in a little more detail. So I love this quote. This is a quote from a Greek philosopher who looked out at the stars about 2,500 years ago or so, and opined that the stars might very well have different worlds orbiting them, each with their own life forms and whatnot. And this is a wonderful sentiment, and it has, in fits and starts, made its way through history to today's era. One of the other proponents of this idea was somebody you may have heard of, Giordano Bruno. And Giordano Bruno speculated that there might be other worlds and that each of these other worlds might have their own Christ, for example, and that was considered very heretical by the church. But he had many other heresies and many other ideas that were out of the mainstream. And for his ideas, for his thinking and saying things that other people didn't like, he was burned at the stake. So, fortunately, we don't do that today. Should be free to say and think whatever you like, and then you submit that to scientific scrutiny to say if your assertion, if your supposition is in fact concordant with reality. Well, we now have enough tools in our arsenal of scientific instruments and the level of education that we've attained across our societies to be able to put Epicurus' assertion to the test, and we're going to be talking about that today. Now, I have a super secret agenda, and this is sort of the agenda that I have anytime I talk about science. This is why being a science communicator and a science geek is important to me in general. My assertion is that there are many definitions of science, right? Some of you have learned one of the versions of the scientific method where you make a hypothesis, you test the hypothesis, you wiggle your hypothesis around and make a new assertion and all of that. But I think there's an even deeper way to view the reason we do science. And that's because we're all trapped in our own minds, in our own heads. Each of us has to learn everything from scratch throughout our lives. Each generation has to learn what's real and true. Some do a better job than others. But when we do that, we're creating in our minds a model of reality. Each of us has a model of reality. If I dance, will it rain? Right? If I seed clouds with dust particles of silver, will that help it rain? If I pray, will it rain? Well, one of those things has had a measurable and demonstrable physical outcome. So one of those potential models of reality corresponds with what nature exhibits. Right? So one of the ways that I like to characterize science is that it is an asymptotic, with a P in the middle of the word, asymptotic approach to a perfect description of reality. So over time, our models of the way the universe works hopefully get better and better and better, such that the difference between what we think is true and real and what we can consistently measure as being true and real, that difference becomes negligible. And different fields of science are at different places along this curve of scientific insight. And that's why it's the subtext of today, because solving the Drake equation, or attempting to solve the Drake equation, is all about reducing our ignorance about many things regarding the universe at large. So let's start with a simple example. You can believe that trees are always flat on top, right? If you live in this place, I believe it happens to be on the island of Madagascar, if you live in this place and these are the sorts of trees you see, then it's perfectly reasonable to assert that the trees in the world are all flat-topped. If you live in this kind of place, which is Switzerland, you might assert that the world is full of big pointy rocks called mountains and hills and covered in coniferous forests, pine and whatnot. So depending on where you live, what part of the world you see, you may come to very different conclusions. If you travel in an airplane, even in a place that locally may look hilly, you might very well come to the conclusion that the world is flat, right? If you're laying the foundation of a building, if you're playing soccer, many things we do in our day-to-day lives are predicated on the idea that the world is flat. Every time you play pool or do some kind of game on a flat surface, you're assuming that the world is flat, that you can do that. You don't have to worry about the curvature of a table when you're calculating how to kick a soccer ball or whatnot. So to a first approximation, it is perfectly legitimate to say the world is flat, right? But as our sense of scale and our sense of place expands, we eventually come to realize that our initial assumption is in error. The world is not, in fact, flat. And this characteristic of the world, that it becomes spherical, we see this recapitulated in nearly every astronomical body we look at, whether it's other planets in our solar systems or other stars, and that's because gravity is a force that works unidirectional or omnidirectionally across every one of the 3 dimensions of space, and you end up with spherical clumps of matter. They get big enough, massive enough that the gravity causes them to compress into spheres. So we see spheres everywhere in the world. And now we have a physical understanding of why that is, right? It could have been, maybe, that the world would be a big tetrahedron or a rhombus or something. But it isn't. And a reasonable question, once you find out the nature of a thing from observation, this is round, the next question is, well, why is it like that? What causes it to be like that? Is there some underlying principle that explains the roundness of the Earth? And if so, is that principle operative at other places that we can see? Even places so far away that it takes light millions of years to reach them. So, let's get back to the Drake equation. The Drake equation begins with a term about the amount of star formation in our galaxy. Now, these are Drake's original estimates from 1961. So, rate of star formation 1 per year, the fraction of stars with planets, maybe 20%, maybe 50%. He thought he might be a little generous about that. The number of planets that could potentially develop life, maybe 1 or 5 planets per star. Again, these are just wild guesses. Back in 1961, we didn't know that there were planets besides the ones we could see in our solar system. And if we can see 8 planets in our solar system, then maybe 1 of them could potentially harbor life. Maybe 2. There are arguments that Mars at one point could have hosted living things. 100% of these planets, according to Frank Drake's original estimate, 100% of the planets that could develop life will develop life. Right? That's kind of Is that Murphy's Law? Anything that can happen will happen? Yeah. And then, again, he was optimistic. He said, well, if life develops, then it is inevitable that intelligent life will develop, right? Apparently he wasn't a biologist or a political scientist. The fraction of alien life forms that might be able to communicate, to develop advanced technology. He made an estimate for that fraction. And then finally, what is the lifespan of a civilization? Oh, I don't know, somewhere between 1,000 and 100 million years. That sounds reasonable, right? So these are Frank's original estimates. But remember that curve. We're now 50 years further along in our pursuit of understanding how our models of reality correlate to what we can see and measure. And I'm not going to say where Frank Drake started with his estimates. Maybe it was somewhere down here. Maybe for some of the things it was down here. Again, back when Frank Drake came up with these estimates, we didn't know about any planets anywhere outside of our solar system. So that speculation was grounded in a model of reality that really had no data to back it up. It was just a pure speculation. Let's now take a more in-depth look at the terms in the Drake equation. The first one is the rate of star formation per year. I think this is a little looping image of the Spitzer space telescope. The cool thing about the Spitzer telescope is that it views, it receives infrared light, and infrared light tells us whether things are hot or not. And when stars are forming, they get hot, right? But they're not as hot as the visible stars that we can see glittering in the night. So having a telescope that is sensitive to heat, to couple that information with data from other telescopes that can see stars once they've been formed, this can tell us about the life cycle of stars and help us identify stars that are being newly birthed in our cosmos. Where in our galaxy are stars born? Right? In star maternity wards.
Big stores.
Yep. This is a star maternity ward, otherwise known as the Orion Nebula. It's a giant cloud of gas and dust in the constellation Orion. It's what you perceive with your unaided eye, or with your glasses aided eye, as the middle star in the sword of Orion, the constellation. But if you use even a modest telescope to look at it, it's this big fuzzy dot. Now through a telescope, it'll look green to you. That's because of the way our eyes respond to dim light, etc. But it's this giant cloud of mostly hydrogen and helium and a few metals, right, metals. Our galaxy, the bulk of our galaxy, is fairly enriched with things like carbon and oxygen and nitrogen. If you've heard of those kinds of elements before, carbon, nitrogen, oxygen, hydrogen, those are also the same kinds of atoms that we use when we construct organic material. And in fact, surveys of the Orion Nebula have found that organic molecules, just that naturally come together because of the way chemistry works, are in fact located in the Orion Nebula. And this really bright area of the nebula here is many light years across. Probably, I don't remember the exact number, something like 100 light years across, really big. But it is populated by a dense nugget of glistening newly born stars, because the gas, under the influence of gravity, has collapsed down, and it sort of fractionalizes off into little globules that turn into their own distinct stars. There's a rule in astrophysics called Jean's law that dictates how globules of gas, how big they can become, and how they, what the limitations are in star formation in terms of size given an amount of gas. But using the Spitzer Space Telescope and other mechanisms, we've been able to assess what the rate of star formation is in our galaxy. And the answer is it's somewhere between 1 and 3 brand new stars come into existence every year. That's pretty cool. All right, so that's that term. We're done with that one. The fractions of stars with planets. Now, I first gave this talk back in 2013, so this particular graphic, because of the hours I spend putting my slides together with all the animations and whatnot, I didn't go back and change this graph. I've changed some others, but as of 2013, look, these orange bars are the numbers of planets that are known outside of our solar system. And, you know, there's a few here, there's a few there, and then all of a sudden in 2013, wow, what happened?
A lot.
A lot happened. Why did a lot happen? Do you have any idea?
A lot of telescopes and things are launched to find those planets.
A lot of telescopes launched. Very, very close to the perfect answer, which was a particular telescope called the Kepler telescope. And the Kepler telescope had the specific mission of staring at a piece of sky that was smaller than a postage stamp held at arm's length. Right? And in that area of sky, the Kepler telescope just stared at it. The thing is, when that happened, the Kepler telescope could compare the images of the stars that it saw from that time into the future. It could compare the stars it saw last week with the brightness and characteristics of the same stars that it would view a month later or a year later. And by carefully monitoring that star, it could look for events consistent with maybe a planet moving in front of the star and causing its light to dim. Or maybe the star would wiggle a little bit under the tug of heavy planets, right? And that and some other mechanisms combine to just cause an explosion in the number of verified what are called exoplanets that were detected beginning in the 2010-2013 time frame. Here's a picture of Kepler. Kepler, I think about 2 months ago, finally, oh, I'm sorry. Yeah, they turned it off. It ran out of fuel. They couldn't keep it stable anymore. So Kepler has done its job, and there will be subsequent telescopes that do something similar. One's called the James Webb Space Telescope. And in any case, from a statistically relevant standpoint, it's fair to say that every single star in our galaxy has a planet. Here's one of the reasons we can say that. In order for Kepler to detect a planet around a star in that tiny little region of space it was staring at, that planet needed to be aligned with us in such a way that the planet moved in front of its host star to cause a little bit of dimming. Well, planets could be oriented in any kind of orbit. They could go around like this so that we could see it, but they could also go around like this, and we would never see a dimming of a star if a planet went around its star like this from our point of view. And if the planet were relatively lightweight, a puny little planet, kind of like Earth, then we wouldn't see its gravitational tug on its host star. So taking those statistically likely anomalies into account, it's pretty likely that every star, or very nearly every star we can see in the sky, has at least one planet around it. Isn't that amazing? And that's something we've been able to determine in the past couple of decades just because of the advances in astrophysics and astronomical tools. Now, I know all of you are excited to see a picture of an exoplanet, so here it is. This is Fomalhaut B, and this is zoomed in on it right here. This is this little box. This is the star. It looks like an eye, not an evil eye, perfectly beneficial, benevolent eye. The reason it looks like this is because the telescope that took this used a special obstruction to block out the bright light of the central star. This is not the central star. This is just an artifact of the way this was constructed. But this ring of dust is real. This is a ring of dust. This is a very dirty solar system. And over time, they took images to show that this one little dot moved from year to year. Now this is why being a scientist is really hard work. I mean, can you imagine looking at similar images from many stars, and you're looking for a little dot that moves from year to year? Now, fortunately, we have computer programs these days that can help do these sorts of very labor-intensive manual tasks. But sometimes it's really hard to squeeze a little bit of information out of the universe and into our own minds. This is the scale of the Fomalhaut system. So here's that image with its dust ring. And that's how it compares to the size of our solar system. So our solar system could be compressed here. This is what's called the Kuiper Belt, which is where a lot of comets come from. Pluto's out here somewhere around here. But all of this could be compressed into this little area here. And this dust ring we saw around Fomalhaut is much larger than the furthest object that we've seen in our own solar system. So it's very, very cold where that planet, Fomalhaut B. Now, for those of you who are budding astrophysicists, a little bit about nomenclature. When you have a star in a constellation, like Ursa Major, which is the Big Dipper, when you have a star, stars are given uppercase Greek letter designation. So Alpha Ursa Major is the brightest star in Ursa Major. Beta Ursa Major is the second brightest star, from our perspective, in the constellation Ursa Major. That's always a capital letter. And then planets, the astronomical community has decided that planets will be designated by lowercase Latin letters, so A, B, C, D, E, right? So whenever you see the name of a planet, it'll often be called something like Fomalhaut B. Now, there are a few stars that are so bright that they have names, usually derived from Arabic names, because there was a period in history when almost all the science and astronomy that was being done in the Middle East by people of Arabic descent. So we get a lot of our star names from Arabic words, and there's a few stars like Vega and Sirius and whatnot that have names rather than Greek letters, in addition to the Greek letter designations. But whenever you see the name of a planet, you're likely to see it named with an A, B, C, D, E, F, G, etc., because that's the way we name planets. Pictures of planets. Here's another picture of a planet. Now this is a star that's so dim that it doesn't even get a Greek letter. It just gets an entry in a catalog of stars, and this is the catalog number for this star. And these glowing dots are 3 planets around that star. It was discovered by 2 telescopes called Keck and Gemini. Each of these planets has a mass of 4 to 7 Jupiters each. Another thing about this particular system is that its central star is very variable. So it gets bright, and then it gets dim, and then it gets bright, and then it gets dim. Could you imagine if our sun did that? It would be unpleasant on our planet. So life would have to be very peculiar to be able to survive in an environment like that. Here's another picture. This is Beta Pictoris. So Beta is the star that's been blocked out. And B is the second planet discovered around Beta Pictoris, and it's 63 light years away. This is the planet. A direct image through a magnificently large telescope. Here's a bit about planet sizes. Here's different planets. They're just to scale with Jupiter, so we can see that many of them are much, much larger than Jupiter. And then we start finding some planets that Kepler has discovered that are smaller than Jupiter. And here's Earth, and we even get a planet that is comparable, several planets that are comparable in size to Earth. This is a count of the number of planets discovered with various masses of Jupiter. So that the number of Jupiter mass planets, so corresponding to 1, something like 200. Again, this is 2013 numbers. It's been upgraded since then. But there's even some planets discovered. Here's a planet that's 13 times the mass of Jupiter. Over here's a little blip for a planet that's 18 times the mass of Jupiter. And quite a few planets that are less than the mass of Jupiter. It doesn't mean that you have a planet with 0 mass. It's lighter than Jupiter. So here are the planets in our solar system. And this is an image that's to scale. So in this image, this is an image to scale. And we see the size of the sun compared to the size of Saturn and Jupiter. And Earth and Venus and Mars and Mercury are all in here too, but they're so tiny you may not be able to see them. So stars are really big. Planets are much smaller than stars, but even a planet like Jupiter is hundreds of times larger in terms of its radius than Earth is. So planets can vary quite considerably in size. And back in the early 1980s, 1970s, this was all the planets that were ever known. And here we can represent them schematically. This is the relative sizes of the planets in our solar system. And then we can compare this to the planets that were known in 2013 and the sizes of those planets. This is a wonderful graphic I found on the internet by the fellow who makes a comic called XKCD. So this, as of 2013, is the number of planets and their respective sizes. See, we're just a small blip in the cosmos. And then here's data from now, 2018. And this shows the planet counts. And this was the spike in 2013. This is where my prior graph ended. And then look what happened in 2014 and 2015, and then a whole bunch of new data was analyzed and were shown to be valid instances of exoplanets in 2017. And these are the different mechanisms that astronomers have used to identify the existence of planets. And I could explain, if you want to look at that for a second, when we get into questions and answers later, if you have any questions about these techniques, I can talk about. Lots of planets. So something like 3,000 or more exoplanets have been verified, and there are many other candidates where we need more data to definitively say that they exist. All right, here's a new twist: inhabitable moons. So if we were to try to live on our moon, we would find it very challenging. And the main reason, the number one reason it would be hard to live on the moon is because gravity is so weak. Everything else taken into account, there's water frozen in craters at the lunar poles. It's close to Earth, so it can get soybeans and corn, etc. But the number one challenge to living on the moon is that its gravity is so weak. In fact, it is so weak. How weak is it? It cannot grab onto an atmosphere. So if you're going to live on Mars, you're going to need to live in a bubble, either a bubble of air on your back that you can breathe, or in some artificial dome, etc., or in a spaceship, or a colony that is fully enclosed, something like a submarine in the ocean. Because the moon isn't massive enough to have enough gravity to contain an atmosphere. Now, why is it that we've got little tiny moons? This is an example, I forget which moon this is, it might be Enceladus, or one of the moons out around another planet like Saturn or Jupiter. And that's a tiny little moon, but it has a thick atmosphere. Well, that proves that I was lying. right? You can have atmospheres around small moons. But there's a trade-off. Remember those differential equations I was talking about? That relates the rate of change of one thing to the rate of change of another thing. Well, one of the things that can be changing is the amount of heat that you get from your star. And if you're far away from your star, the amount of heat is low. Well, if it's a low amount of heat, then you're able to have an atmosphere in a colder place because it's the starlight, the heat of starlight or sunlight, that would cause the atmosphere to literally boil away. Okay? So, a planet or a moon that's relatively small, that's far away from its host star, can still have an atmosphere. But our moon, which is in a nice area where it's comfortable for us and most other living things because you need liquid water, our moon cannot have an atmosphere. But there's this planet around this Eta. I think I'll know its name in a second because I have it on a slide. What's that Greek letter? Is that it doesn't matter. There's mu Andromedae D. So D again is the little lowercase for the planet. And the Greek letter, oh, I'm sorry, they sometimes use lowercase Greek letters too. Upsilon, that's it. It is Upsilon. Upsilon Andromedae D. So this is a planet, and it's a really giant planet, bigger than Jupiter. But interestingly enough, we've been able to detect that it's got a lot of water in its atmosphere. But it's so big and heavy, it's probably not a very hospitable place. But this is the giant planet over here, and if we don't know for certain, but if there are moons around that giant planet, it's plausible that those moons could have water and an atmosphere. So it's plausible that life could evolve on a moon rather than a planet. And the distinction is kind of academic. You know, we use our words to describe moons and planets. Another word for some of these could be a binary or a multiple planetary system. Some astrophysicists argue that the Earth-Moon system is actually a double planet rather than an Earth and a satellite. I think the barycenter for the Earth-Moon is outside the surface of the Earth, so the common center of gravity is outside of the Earth, and that may be one of the characteristics they use to decide if it's a multiple binary planet or trinary planet, etc. Another technical digression. But imagine living and evolving a civilization on a planet, or on a moonlet, a moon, that has a gigantic planet in your sky. Pretty awesome for photographic opera. Imagine all the newlywed pictures. One of the problems with that particular planet and its moons is that it orbits around something called a red dwarf star. And some of you have heard me talk in the past that red dwarf stars tend to be pretty violent places. They're all frothing and boiling and emitting giant sprays and storms of dangerous radiation. So, maybe there's nobody there. We don't know. We haven't been able to look closely enough to evaluate for certain. This is a wonderful thing that just came out a couple years ago. You've heard of the periodic table of elements. There's an astronomer, Dr. Abel Mendez from the University of Puerto Rico, who has come up with a periodic table of exoplanets. This is really awesome. So you've got mini planet. I call it a mini planet. You've got many little planets that are they're really hard to detect because they're small. And then you've got ones that are a bit smaller than Earth, but not mini planets. And then you've got planets that are about the size of Earth. And then you've got ones that are somewhere between Earth and the size of Neptune. And then you've got ones that are Neptune and larger up to the size of Jupiter. And then you've got the Jupiter-sized and larger planets. So these are the categories of planet sizes. And then over here, along the left-hand edge, is the relative temperature, the ambient temperature of those planets based on how far away they are from their host star. So this is a nice way of seeing Earth-like planets in the hot zone of a star, probably not hospitable to life. Earth-like planets far away from their star, probably not hospitable to life. I've had other talks where I talk about the importance of water to life, etc. But right here is the Goldilocks zone, and that's what it's called. The Goldilocks zone, where water can exist as a liquid. And we, humanity, I don't mean me, I've never done any of this, but humanity has discovered potentially habitable planets around the Goldilocks zones of distant stars. That's really exciting. And that's one of the reasons that some of the new telescopes that are being built at an expense of millions and sometimes even billions of dollars are being built specifically to look at these planets, to see if by looking at them and trying to resolve their chemical properties, if we can ascertain whether or not they have things like nitrogen and oxygen in their atmospheres. Okay, so going back to the Drake equations. The number of planets and moons that could potentially support life per star system, well, based upon that periodic chart of exoplanets, it's somewhere between 0.5% and 3%. Well, that's a pretty big variation, but it's a lot better than a stupid guess, right? So again, the reduction of scientific ignorance. New planet hunter telescopes are coming online that will help us discover even more planets and maybe narrow down this number even better. Okay, the fraction of life-friendly planets that actually develop life. Well, now we're getting into science speculation, or some would say science fiction. Here are some criteria that many scientists have argued are necessary for the development of life on Earth. Plate tectonics. Plate tectonics on our planet recycles a lot of material that is useful for life, including water and carbon, among others. A large shielding, orbit stabilizing moon. Maybe a moon is important. Not only that, many of you have heard me say over the years that the collision between these two early planets in our solar system that led to the development of Earth and our moon, we believe it's the result of a collision. If that collision had not happened, then maybe we wouldn't even have plate tectonics. So maybe a moon is more important than just being out there as a shield in the sky. And recently, about 2 weeks ago, I saw a science article that said that some group of scientists, astrophysicists, have speculated that any Earth-sized planet with a large moon likely has that moon because of a collision like this. They say that that's how they think these large moons, like our moon, could come to orbit an Earth-sized planet. Well, that's just a speculation. Again, we don't have the evidence that we've been able to validate that speculation. But if it's true, if having a moon is important, and if those moons only exist because of collisions, it's a rare event. A hot core is useful. It drives the engine of plate tectonics, as it were. It also helps with the magnetic field. I'll get to that in a minute. A thin crust. Without a thin crust, you couldn't have plate tectonics. You couldn't have volcanic vents that produce geothermal heat sources that might be implicated in the origin of life on our planet. It may be, well, it is certainly true that the first life on our planet was not photosynthetic. It didn't use sunlight for its energy source. It likely used geochemical processes. So a thin crust to allow volcanoes to poke through is useful. A magnetic field. Here's a $5 word, eukaryotes. That means complex cells with a nucleus and a membrane and other things. Everything you can see, every living thing you can see with the unaided eye is a eukaryote. It's built up of multicellular structures, and those cells are all eukaryotes. But eukaryotes are fairly fragile compared to things like bacteria. So it may be that a magnetic field is necessary to shield a planet from radiation. Some recent studies have shown that the ionization of the upper atmosphere by solar rays could also produce a kind of shield. So maybe you don't have to have magnetic cores to get shielding. And then an ocean, right? Water is really important on our Earth. It helps stabilize climate. Water is implicated in all the biochemistry we know for living things. So an ocean may also be necessary. Here's a schematic, or here's a representation, a cutaway diagram of the way our Earth looks. There's nothing magical or mysterious about the Earth. There's no reason at all that similar planets could not exist in great variety out in our galaxy. So here's artistic rendering of the event that created the moon, a proto-Earth colliding with something about the size of Mars and gave rise to the moon. In any case, the terms of the equation, the fraction of life-friendly planets that actually develop life. We have no idea. It could be close to zero. Maybe we're the only one. Or it could be that there are a lot of them. One in this case means 100%. We don't know. Scientific ignorance. Okay, consider, for example, that life seems to have evolved only once on our planet. All the life on our planet uses DNA of a similar sort, right? So maybe it's a very rare circumstantial thing that causes life to emerge from non-living geochemistry and physical processes. We don't know, and that's okay, if a bit frustrating. So we're looking, one of the good candidates to see if the origin of life, the generation of life from geochemical processes, is perhaps more common, is to look at Mars, to see if Mars ever had life on it. If it did, maybe it came from Earth, was seeded from Earth, or maybe it evolved and developed independently. That's one of the reasons we're spending so much time and effort looking at the soil and rocks and whatnot on Mars to see if there's any evidence of microbial life in the past. Okay, the next term of the equation, the fraction of life-bearing worlds that develop intelligent life, right? There are, some say one, some extend that to say a handful of intelligent species on our Earth, right? Maybe a climate catastrophe was necessary. Maybe the great extinction events that happen in our particular history are important. Look at the number of millions of years that dinosaurs were around, and no advanced intelligent society ever developed from dinosaurs. And looking at the size of dinosaur brains, there's no evidence that dinosaurs ever developed a capacity for complex social and intellectual lives based on their brain anatomy. You have to be in a relatively safe part of your galaxy so that there's not giant swarms of meteorites and dusts and comets, whatnot, pelting your planet. Consider that with billions of species that have ever existed over the history of the Earth, only a handful are intelligent, and you begin to see the challenges, right? I mean, it's pretty safe to say that dolphins and elephants are intelligent, but they're not technologically advanced. When I talked last time about having tentacles, right? The ability to manipulate your environment is one thing. But in any case, the evolution of intelligent life seems to be pretty rare. This shows the evolution of life. This transition from simple bacteria to eukaryotic life, there's that word again, to the kind of cells that allow multicellular organisms, that seems to have happened about, let's just say about 1 billion years ago on Earth. And what if you're on a planet where that never happens? That chance meeting of two different primitive organisms, like a bacteria and a related thing called an archaea, where they come together and decide to live peacefully as a community rather than destroying one another, right? What if that chance event never happens? We don't know how likely it is or how unlikely it is. So even the evolution of large, complex creatures, multicellular creatures, is something we have no idea about how likely it is. Certainly, it's plausible that you can get simple bacteria and whatnot, given the right geochemical conditions. But it took billions of years after that for Earth to have this chance event where a complex cell led to complex life. Maybe it was completely random and highly unlikely. So again, the chance of intelligent life evolving is somewhere between I have no idea and 100%. Yeah, right? I mean, if you're going to ask a question, you just as well put parameters around it. Right, the next term in the equation, the fraction of worlds with intelligent life that develop technological civilizations. I was talking about the tentacles that we use to manipulate our environment. Last time I talked about the importance of fire. Here's some other things, tool-using bodies. What about fossil fuels? Imagine, what if we had evolved on a planet that didn't have accessible fossil fuels? What would it be like to have civilizations whose only source of energy is wind power, river power, and wood, right? The amount of energy you can get from fossil fuels is tremendously larger than any of those, and it's portable. You can put it in machines. You can carry your fuel along with you. You can make flying machines. You can't make flying machines by burning wood, right? You can't make a rocket ship with charcoal. So fossil fuels may be a necessary component for developing advanced civilizations. Isn't that interesting? Accessible metals. And by metals, I mean like chemist metals, not astronomer metals, right? Iron, nickel, copper, etc. Only about 25% of the civilizations that historians have cataloged that have lived on Earth, from the Akkadians to the Babylonians to the Romans, only about 25% of civilizations have shown a propensity to aspire to a systematic technological advancement. And most of those civilizations are around today. Think about the hundreds or thousands of years, think about the tens of thousands of years in human history where everybody was happy just to use the same stone tools. This is the way it's done. That's the way my grandfather did it. Right? And nobody is allowed to or incentivized to think of new things, of a way to make something better. Political statement, we have capitalism, largely to thank for that. But without some social structure that incentivizes, rewards, and inspires creativity and innovation, you can have civilizations that don't have any of those incentives. So you can just trundle along. We did it for tens of thousands, 100,000 years as a species. And then here's another thing that's happening. Our civilization is going dark in terms of radio communications. A lot of the communications that we do now is through fiber optics, point-to-point communications. This idea of broadcasting globally radio waves and TV signals and whatnot, that's being attenuated over time. So maybe there's only a brief period of time when a civilization is beaming I Love Lucy out into space. And if you're beaming a signal out into space, then there's the potential that you can hear the radio chatter of another civilization. Sound waves don't go through space. Semaphore signals don't go through space. Smoke signals don't go through space. The only thing that goes through space is gravity waves and electromagnetic waves. And electromagnetic waves are a lot easier to generate than gravity waves. So we've got all these electromagnetic wave sensing telescopes around the world listening for the chatter of alien civilizations. And nothing has ever been heard definitively. There's a couple of, oh my gosh moments, but those have been explained by natural terrestrial pulses. So again, what are the chances that an intelligent species, we've already gotten past all those other roadblocks, what are the chances that an intelligent species evolves on a planet, technological species? Somewhere between to, of course, again. All right, the last term in the equation, the lifespan in years of a technological civilization. Think about this. We might be able to hear the radio signal of a civilization that says, hey, come join us for lunch. But the distance between the stars is so vast that that signal may have originated from a place such that it took the light thousands of years to get from there to here. Thousands of years. Look what's happened here in the past 100 years. Past 200 years. The world 1,000 years ago was virtually unrecognizable compared to the world. What about getting a signal, a radio signal from a planet that was sent 10,000 years ago? And that's only 10% of the way across our galaxy. Right? So it takes a long, long time for messages to travel in space. So is it plausible that we could have species communicating with each other? A lot of one-way conversations. Hi, here we are, this is what we're about. We like tuna fish and apple pie. And then you wait 10,000 years for somebody to say, oh, you shouldn't eat tuna fish. All right. And then another factor in the longevity of civilizations is self-inflicted or natural events that might lead to the end of civilization as we know it. Everybody knows what that is. I don't have to explain it, right? Still could happen. Giant asteroid impact. Same kind of thing that is thought to have destroyed dinosaurs. Still could happen. This little creature is Ebola virus. Some catastrophic illness that decimates, if not worse than decimating. Decimating means take 10%. Could destroy human civilization. So what are the lifespan of civilizations? Again, we don't know. We're still trying to get this one to persist in a way that's sustainable. So these were the estimates in 1961. These are the estimates in 2013. Some things have gone up. The rate of star formation, he thought it was 1 star per year. We think it's maybe 3. All right? We're making progress. We're making progress, slowly. Some of these other terms, we're going to have to find a lot more data from a lot more planets around many other stars in order to narrow these down. A closing paradox, thing called Fermi's paradox. Enrico Fermi was one of the most brilliant scientists that a lot of people have never heard of. He's the guy Fermilab is named after. And he was involved in many discoveries around nuclear science and whatnot. And he was famously, he had this deep intuitive grasp of the natural world that few scientists could ever hope to achieve. For example, during the atomic bomb test, there's this story that is a true story, it's not apocryphal, where Enrico Fermi, the blast wave came from the first atomic bomb, and he tore out some little pieces of paper and he dropped them. And he waited to see the wind of the atomic explosion blowing those pieces of paper. And from measuring how far those pieces of paper were blown by the wind, he calculated the yield of the atomic blast. Right? That's the kind of just genius. I mean, that is what genius is. Finding, sometimes, physics is notorious for having complicated answers to simple problems. Maybe, sometimes there's value in having a simple solution to a complicated problem. So Enrico Fermi was one of those people. And he said, the sun is a relatively young star. We've had civilizations around, technological civilization, for 100 years or so. But there are stars that are much older than the sun that have rocky planets that might have life around them. Some of these are likely to have civilizations. Maybe some of these will develop interstellar travel, or at least interstellar communication. And any practical pace of interstellar travel, even if it takes you 1,000 years or 10,000 years to get to another star, the universe is really old. So even if you can go to another star and you make a generation ship, or you freeze living organisms, or maybe you've got technology that allows you to live for thousands of years. In any case, the idea is that even at a very slow pace, a technologically advanced civilization, more advanced than our own, could discover other worlds and make themselves known in their home galaxy over a period of a few million years. And a few million years is a blink of the eye in the history of the universe. So his question is, where is everybody? Why do we have radio silence? Why do we see no evidence of other intelligent civilizations? And there have been all kinds of speculative answers to that. I've read a couple of books about that, and I can talk about it if anybody is curious later. But it's a good question. If life has evolved, if technology has evolved, if interstellar travel is at all possible, where is it? All right, so here's a couple of websites that might be interesting to you. And that's it. Thank you. Questions? Yes, sir.
Scott, so if you went back to the thing that was like the periodic table, that visual.
Yep.
Yeah. Yeah. Okay, you went to hot zone big boxes and opened up the extreme files. Would anything really change?
Extremophiles, does that change anything? Yes. Okay, an extremophile is a form of bacterium or archaea. They're very closely related. For the sake of disposition, let's just say bacteria. An extremophile is a bacteria that has been able to develop a biochemistry that it can survive in extreme environments, extremophile. They love extreme environments like boiling water or things that are rich in acid, acidic pools, etc. So the question is, do extremophiles mean that advanced life might be plausible on some of these other, what we consider inhospitable planets? Maybe, but every extremophile that has been discovered on Earth is a prokaryote. It is one of those simple bacteria or archaea. One of the cool things about biology is that if you want to do innovation at a biochemical level, then microbes are your ticket. Bacteria and archaea are good at evolutionary tasks that involve solving biochemical puzzles. Eukaryotic life, multicellular life, is good at evolving organisms that solve mechanical and physical problems. We have inherited within the structure of our cells the legacy of microorganisms that are good at metabolizing carbon and oxygen and whatnot, and those are plentiful things. Is it plausible that a complex cell could evolve on a planet that has much more inhospitable environments? I'd say it's just at the edge of plausibility, but not very likely. No.
What's the shielding property that the moon has on the Earth that you mentioned?
So early on, 3 billion years or so ago, the Earth was formed about 3.8 billion, or somewhere around there. Was it with 4.5? Yeah, 4.5. It's 13.8 for the universe and 4.5 for the Earth and the solar system. The moon started off it was a collision between the Earth and this other thing, right? And the moon started off very close to Earth, and when it was close was during that period when there was still a lot of debris, a lot of crap in the solar system, asteroids and comets and meteorites and whatnot. And by having a large moon that close to Earth, it provided a bit of a shield, right? And it still does to a certain extent today. It also helps clear out our orbit of debris by flinging things out and whatnot.
It also stabilizes the gyroscopic aspect of the planet, otherwise we would tumble.
Right,
And
from the
having
collision.
the moon around us we have a relatively stable
Right.
rotation.
Yeah, for those of you who are science fiction buffs, imagine, I mean, write a story what it would be like to live on a planet with no seasons, where the only variation in climate you would get would be going towards or away from the poles, right? I mean, all of these things are plausible ways that the universe could manifest planets. And it just boggles the mind to think about what that might be like. Any questions? Yes?
When debris was created, which in part became the moon, it was from an impact. So it was a glancing blow, it would have flattened out. It was a direct blow, made a pretty big hole. How did the Earth get around it?
Good question. So the name of that thing that hit the Earth, it has been given a name of Theia. When Theia hit the Earth, both objects, both the Earth and Theia, became these molten blobs. And there's some pretty justifiable speculation that the moon consists almost entirely of the same kind of material that is in the crust of the Earth. It has very little iron and nickel, very little of the molybdenum and some of the heavier elements that go into creating complex minerals on Earth. So the speculation is that after this hit, there's just sort of this blob that blobbed up from the surface of the Earth, the crustal material that became the moon. So we really are a composite planet. It's not like Theia and Earth were distinct and have always been distinct. They've merged. And we burped off a big blob of this material that's like the Earth's crust, the lightweight stuff, blobbed out into space and became the moon. And what caused it to become spherical again? Well, it's the same thing that caused us to be spherical in the first place, gravity. Yes?
Somewhere along the line, Scott, I read something about all binary stars, trinary stars, where stars are around the plane of where most stars are around the center of our galaxy, being too close to the center of the galaxy. So does that, anything like that, shift the odds in terms of even if those stars have planets, that they don't stand a chance unless they
Yes.
have things that can like deal with radiation or something?
Yeah, there's a habitable zone of our galaxy, just like there's a habitable zone around our sun, our star. And it's thought that closer in, as you get closer into the center of our galaxy, things become a lot more energetic. You get a lot more high energy radiation and collisions. And in astrophysics, collisions where one thing literally hits another thing is very rare. Space is big and it's mostly empty space. So in astrophysics, it becomes relevant when you have things nearby each other. You know, they orbit and they do this, and then they separate at high speed or whatever. These sort of mutual interactions. You don't have to have things touching or slamming into each other to have a collision. When galaxies collide, it's not like the stars splat up against each other, right? But it's the complex of orbital dynamics that comes into play in some regions of our galaxy. And those same complex orbital dynamics are relevant when you have multi-star systems. You could have a planet that's in a stable orbit for millions or billions of years, but eventually another star tugging at that planet could create a stochastic or a kind of random effect that eventually causes a planet to be ejected. So those are really important considerations. Whether you could have a stable, hospitable environment around a planet that's in a binary or multiple star system. That's a good question. I don't have a clear answer, but I'm sure people have written all kinds of papers about that. Mike?
This is a question about a huge gap, it seems, between simple amino acid type molecules and complex molecules, complex enough to be like, I mean, to reproduce and so on. I mean, even a bacteria has DNA in it, right? And they're very complex molecules. So the process by which the simplest of reproducible life molecules, I think we don't know anything about that. Do you have something to say about that? I mean, there's a huge gap in our understanding, I think.
Yes, I can tell you how life was created, of course. I have a talk that's up on YouTube many of these lectures are on YouTube, and I have a talk about the origin of life. In 2 minutes, if I can encapsulate the original idea, at the center of the metabolic process of nearly every cell is a thing called the mitochondria, and this has what's called a proton pump in it. And it takes advantage of slight electrical gradients between ionized hydrogen and other chemicals to create a force, an electrical force. And that electrical force of protons is the force at the heart of life. Well, in the mitochondria, if you look at the chemical reactivity and the way that mitochondria carry out their business, there's a little iron-sulfur complex, molecular complex, that's implicated in that action. So that leads biochemists to the speculation that the very first metabolic life on Earth was in an environment that had sulfur and iron. Well, that's deep sea vents right now. We think that that's deep sea vents. But I think, this is my own idea, the tides were much more significant. Remember, the moon was much closer back then? So the tides were much more significant. And there are other groups of scientists who speculate that periodic drying and wetting of something like clay was implicated in allowing complex molecules to form and then dry out, because a lot of biochemical processes are hydrophobic, right? So they can emit water as part of their interaction, but if you're already surrounded by water, maybe that reaction won't help. So there's all kinds of speculations about the environments in which those chemical processes first arose. But think about a big moon causing huge tides and a baby Earth that's fractured, has its crust fractured by recent collisions and whatnot. So you might have something like an aquatic smoker vent bubbling up hydrogen and iron and sulfur and whatnot in an area that's essentially also a tidal flat, right? What's to prevent what we now see deep sea smokers? Back in the early history of the Earth, the geologists say that there were no giant continents, there were these little island chains, right, that came together eventually to form continental cratons. So it's a big complex question, but the idea essentially is that there were different circumstances on the early Earth that is like nothing we see around us today. And it is plausible that metabolic processes evolved or were first instantiated around a source where there's a natural chemical gradient, geochemical gradient. And that got encapsulated into a self-replicator. There's these speculations about DNA worlds and other things. So it's an incredibly complex question, and I probably can't even do it justice. But people are thinking a lot about it, and they have some very tantalizing ideas about how it might have happened. Yeah?
Can you say more about the idea of us being actually, the Earth and the Moon being a biplanetary system?
Binary planet?
Yeah.
So in orbital mechanics, there's this idea called a barycenter, B-A-R-Y-C-E-N-T-E-R, barycenter. And the barycenter is the center of gravity for an interacting system. And if I'm remembering correctly, and I may not be, but if I'm remembering correctly, if the barycenter of a system of gravitationally interactive objects is outside of the physical body itself, then that is a plausible criteria for saying that it's a multiple planet system. If it's a very small moon with less mass, then the barycenter between Earth and right as they orbit, the Earth orbits the moon a little too. They both orbit what's called the common barycenter. And if that barycenter is located outside the surface of the Earth, then that's a criteria some astronomers use to say it's a multiple planet system. It's just a technical thing.
Okay, so what actually happens in the barycenter? Normally, if you think of a center, it would be the most powerful area. That's not the case because people float in space. So, what happens in that? What is that barycenter?
It's just a geometric point that is the weight, mathematical, I say weighting, but we also use weight in terms of gravity and mass. It's the mathematical weighted average of the mass distribution between the Earth and the Moon. It's just a mathematical point. There's nothing physically special about it, except it is the point around which both the Moon and the Earth can be said to orbit. Yeah.
It's still in the Earth.
It's still in the Earth? Okay, thank you for looking that up.
Still in the Earth, yeah. It was sort of wild.
Yeah, the Earth does wobble. Okay, thank you. I'm sorry. Do you have a comment, question?
No, I was just gonna say what you already said.
Okay.
About how, like, it's becoming a point where they go from here to orbit or not.
Good call.
I read an essay, Scott, 2 years ago by Stephen Weinberg, who argued that in the Obama administration, the Webb, James E. Webb, would be funded to exist, but funded never to be launched. They show tapes and doesn't matter.
Oh.
Do you think it ever will be launched?
Yes. Yes. I was thinking about this in the shower the other day. The James Webb Telescope is kind of the successor to Hubble and all that. I do some of my best thinking in the shower. We're all American. And, right, the James Webb Telescope is still in a hangar being built, and it's had billions of dollars thrown at it, and more billions of dollars that nobody ever thought should be expended, but it, and now, fortunately, on our side, we have a logical fallacy called the sunk cost fallacy. And the sunk cost fallacy says, well, we've already spent $10 billion, what are we going to do, just let it sit there? No, we just as well spend another $3 billion and get it up in space, right? So I think we've got this sunk cost fallacy going in our favor, and my speculations in the shower were, is that really a sunk cost fallacy at that point, if it actually inspires us to do something, innovative? So, yeah, I think that James Webb Telescope is going to go up.
It may go up privatized.
Yeah, could be.
There's a lot of push. Just this past week, NASA's been pushing really hard about privatizing a whole lot more space exploration, including moons, establishing a moon base
Okay.
as a starting base for Mars, privatizing almost all of that.
Great. All right, I'll be around for a few minutes. Thank you.